Okay, so yesterday we started talking about oscillators. First, we talk about classical oscillators, where it's just like a simple pendulum. It can keep moving in a harmonic well. And then we derived the partition function for it. We derived the heat capacity for it, and that turned out to be constant. So then we looked at a quantum harmonic oscillator. I will recap what's the idea behind quantum harmonic oscillator. I will not go into the energy eigenfunctions. If quantum mechanics sounds strange to you, well, you're not the only one, and also I cannot solve that problem. So I can only use the results from quantum mechanics. I'm not going to prove the quantum harmonic oscillator for you, and that's why I posted the Wikipedia article. And so we will talk about the quantum harmonic oscillator partition function. We will talk about a very important concept known as phonon density of states. And if you're doing any sort of scattering experiments ever, the density of states is a very, very fundamental quantity. And then I will show you Einstein's approximation to this density of states. Then I will show you Debye's approximation to density of states. Einstein was kind of lazy, at least in this one. Maybe he was writing so many papers. So his model does not get it quite right. His model gets the key idea right. Einstein's model also gives us that the heat capacity goes to 0 as temperature goes to 0. But Debye's model does a much better job. So that's what we are going to do today. And I want to point out that Thursday, March 16, the class will be only in person, no Zoom, live or recorded. And it will be taught by a very, very special person. It kind of looks like this. Simon is laughing. Does he have glasses? Yes, he has glasses. He's sitting in the back. It's over there. So that's, why don't you introduce yourself? Come on, man. Don't be shy. So that's Doc. No, you're gonna go on the faculty market this year. What are you talking about? I'll write that in the letter of recommendation. No, and which section from Chandler are you teaching? You remember? So he will be teaching section 4.4 from Chandler, which is fermions and bosons. So that's why he will be following it to the dot. See, he's mega nerd. That's fine. So he will be teaching on Thursday. I won't be teaching, and it won't be live. So please try to come in person. It will be easier than today's class. So let's talk about harmonic oscillator. So in classical mechanics, if you're thinking about an harmonic oscillator, and if you're thinking about U as a function of R, it looks like it's a harmonic oscillator, so it looks like a parabola. And you can oscillate as much as you wish, right? Any small difference in energy is possible because it's classical mechanics. Quantum mechanics says that instead of this, you have to think about E, which is a sum of the kinetic energy and the potential energy. And that E is actually going to be quantized. You cannot take every possible value. You can take only discrete values, which are given by E alpha is equal to U naught, which is the stability binding energy of the crystal. It's some negative number. We set it to be 0 for convenience later on. U naught plus N alpha plus half H cut omega alpha. So omega alpha is the curvature over here. And the reason in quantum mechanics, what does it mean to draw such a well? That for it, in order to really understand that, you have to look at the wave function. So it talks about the spread of the wave function, right? But we are not going to get into the eigenfunctions. We are going to use the energy eigenvalues. So these are the quantum mechanical energy eigenvalues. They are discretized. And that's intuitively, we already see why the heat capacity. So what are we trying to explain here? The big picture that we want to explain is that heat capacity versus temperature looks like this as per experiments. At very, very high temperature, it becomes 3n multiplied by k. At low temperature, people did experiments, and like already in 90, because measuring heat capacity is not that hard. I mean, even I have measured it in undergrad. It's like the only experiment I was ever able to do. This is really easy. And if you measure it as a function of temperature, for almost all materials, it turns out that the heat capacity can be very closely approximated by a function of the form AT cubed plus BT. And that's what we are going to understand. Today, we are going to understand, I don't know how much of this will take time, and this ATQ plus BT is like one exercise problem in Chandler, which is terrible, and it will take us at least 2 lectures to work through it and a lot of math. So this AT cube dependence comes from phonons, from the vibration of the atoms in the crystal. Anyone knows where this BT dependence comes from? Go ahead. Electrons. And there is a big assumption here. The big assumption is that the electrons and phonons act independent of each other. When does that assumption break down? In what kind of chemistry? Is it always true that electrons and phonons live in separate worlds? Why not? Photochemistry, strongly correlated materials, lots and lots of systems, the electrons talk to phonons. When I say electrons talk to phonons, what does that really mean? It means that, so in physics, there is a fundamental approximation, which is known as Born-Oppenheimer approximation, right? Born-Oppenheimer approximation says that atoms move much slower than electrons, right? If Jared is nodding his head most vigorously, I will use it as an example. If I shake Jared up and down, the idea is that anytime he goes up, the electrons relax very quickly. Anytime he goes down, the electrons relax very quickly, right? The time scale of Jared's movement up and down is way slower than the time scale at which electrons are relaxing. But in reality, that's not true. If I shake Jared up and down, the electrons will be like, ooh, what's going on? I don't know. They will be connected with how he's moving, right? So there will be other terms here and that's actually an area of open research as to study materials where there is electron-phonon coupling. That happens in a lot of materials, photochemistry, semiconductors, whatever you can think of, it invariably shows up. But if you go and Google or look up plots for heat capacity versus temperature, ATQ plus BT does an incredible job in capturing it. And ATQ comes from phonons, BT comes from electrons, and we will work in all of, I will give you very good intuition for why these all things happen. So in order to understand all of this, today we will start with the expression that we wrote last time in class, okay? So what was the expression? The expression that we did was to think about the energy of a microstate, right? And in order to think about the energy of a microstate, we went to, actually I have to tell you one more thing, physical, which you might have forgotten. So what is this omega alpha? So the idea here is that atom number 1 can oscillate in 3 directions, X, Y, Z. Same for atom number 2, it can oscillate in 3 directions, X, Y, Z. Same for atom number 3, so on and so forth, right? So you have n atoms, each of which can move in 3 directions. So all I'm assuming is that, first of all, every atom is moving independently of every other atom. Furthermore, X is independent of Y, is independent of Z. Okay, this is an assumption. These are big assumptions. If you have directionality in a crystal or things like that, or in a chemical, X and Y will be coupled. Go ahead.
Why do we need to keep the atoms? Just like keep the oscillators in the ensemble?
Yeah. I'm just trying to give you intuition. If you come from a world where oscillators are more intuitive to you, that's wonderful. Good. Force be with you. To me, atoms are more intuitive, right? So I think about every atom having 3 degrees of freedom. So yeah, the big picture is we are just thinking about 3n independent harmonic oscillators. And earlier we used the classical solution to harmonic oscillator. Now we are using the quantum oscillator. So what this means is that every atom will have a frequency of movement. The first one is moving every atom along every direction, right? So we will have frequencies that go from omega 1 to omega 3n. We don't know what their values are. And this is what will lead us to density of states later. Given any frequency, on top of that, you can have the ground state, you can have the first excited state, second excited state, third excited state. The ground state is when you say 0 phonons along frequency omega alpha. The first excited state, you say 1 phonon along omega alpha. So phonon captures which quantization are you, which excited state are you in? It looks very bizarre. The first time I learned about phonons, I was like, this is fake. It's a fake particle, I know electrons, I know protons. What's a phonon? If you really think about it, it's not that much more complicated than an electron. Have you ever seen an electron? You have done some electron microscopy, so you would like to believe that you have seen an electron, but not really. You have seen some wave functions moving around. It's not,
CRT-TV.
huh?
CRT-TV.
Well, then I'm seeing phonons right now as you're talking. So phonons sound very abstract, but they are actually even more fundamental than electrons, right? Electrons capture quantization of charge. Phonons capture quantization of movement due to thermal motion, right? That's the whole idea, okay? It sounds abstract, but it's quite concrete. And another point I made, which I'm not going to get into today, is that here I'm showing you quantization or existence of phonons in quantum mechanics, but phonons can actually exist even in classical mechanics. And Wikipedia has a nice article on this. For that, you have to think about stationary waves and things like that. So we wrote down for every frequency, we start from omega alpha, omega 1, omega 2, omega 3. We don't know the value of what this frequency is, but for any given frequency, the energy will be given by n alpha plus half h cut omega alpha, where we have said u naught is equal to 0 for laziness reason. There is no other reason. You can keep it if you want. And alpha goes from 1 is equal to 3n. So this is my E nu. This is what I will call equation number 1 today. And with this, I can write down my partition function q of beta and v. That's going to be summing over all microstates, going to that microstate, calculating the energy e to the power minus beta E nu. And so we can write this down. How is a microstate characterized? The microstate is characterized by specifying the values of the occupation number, n alpha, right? N1, N2, N3, and 3n. So we have to specify N1, which can go from 0 to infinity. We have to specify N2, which can go from 0 to infinity. Let me write it down as different summations. So instead of writing it, yeah, so N1 is going from 0 to infinity. So N1 goes from 0 to infinity, N2 goes from 0 to infinity, which is the last subscript for small n? Huh? No, small n. 3n, because alpha goes from 1 to 3n. Yeah, yeah, this can be confusing later. But so we have this, and now we will write e to the power minus beta E nu. What is E nu? That is alpha is equal to 1 to 3n, n alpha plus half h cut omega alpha. So it looks pretty terrible, right? It's like summation of exponential to the power summation, like horrible. Let's work with it and it simplifies. And why does it simplify? Because our oscillators are independent. If our oscillators were not independent, we would be royally screwed. So N1 is equal to 0 to infinity, N2 is equal to 0 to infinity, and 3n is equal e to the power minus beta. What we can do now is to pull out this half h cut omega outside the summation and bring it over here, right? So let's do that. So this will become h cut omega alpha by 2 e to the power minus beta summation alpha is equal to 1 to 3n n alpha h cut omega alpha. Does anyone see what can we do next? Well, yeah. So first of all, we can take this thing and bring it way outside over here, right? That can go up front without any problem, right? The whole thing just goes outside. So this becomes e to the power minus beta h cut omega alpha by 2 summation n1 is equal to 0 to infinity. But if you think about this thing over here, let's write it down in full. So we have n1 is equal to 0 to infinity, n2 is equal to 0 to infinity, dot, 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 n3n is equal to 0 to infinity, e to the power minus beta n1 h cut omega 1 plus n2 h cut omega 2 plus dot, 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 n3n h cut omega 3n, right? Now you have to realize that this summation over n1 contributes, is affected only by this quantity, right? Yeah, go ahead.
In the top equation, we had omega alpha inside the sum, and in its alpha, implied that it goes over every microstate. But-
Alpha denotes the frequency for which atom you are.
So they're different.
They are different. Microstates are gone now. Microstates are accounted by these things, the value of the occupation numbers. So the value of occupation numbers describe microstate. Omega alpha is which atom are you talking about?
So Q is a partition function for specific number.
No, we are now looking at all three N frequencies,
Then
all
how
three
do you-
oscillators.
How do you pull out the omega? Because you're summing over alpha.
Yeah.
Oh, that's a good point.
Alpha outside of any summation.
You were wondering right. Well, you might hate me for that, but I will tell you, you will hate even more if you had a teacher with perfect notes. That's like a robot. Why do you want that? Okay. Thank you, Alex. We have to scratch this. I went too far too soon. Good cop. It also happens, I also think there's a form of familiarity bias. I like this material the most in all of StatMech. So this is where I tend to look at my notes the least. Hence, I make the highest number of silly mistakes. With no excuse though. When Eric teaches on Thursday, it'll be like flawless.
Even the previous step you have to do, because the one with this blue circle,
How about that?
because omega alpha still has to be inside the summation.
Oh yeah, my life is ruined. That's okay. Cool. So let's look at it. Oh no, he's staring. Look at that disgust, that anger. In Zoom, there will be a sound of. Okay, so that's okay. This we will work through this. So let's work with it carefully. So we have N1, the same thing. N1 is equal to 0 to infinity, N2 is equal to 0 to infinity, N3N is equal to 0 to infinity, e to the power minus beta and now it's going to be N1 plus half h cut omega 1 e to the power minus beta N2 plus half h cut omega 2 dot dot dot. Happy, Alex? Happy, Vedant? Good. Now we can take all of this and realize that this is the only thing that depends on N1, right? So this can be brought over here. This is the only thing that depends on N2. So this can be brought over here, right? We can just move this around. So instead of a multi-dimensional summation, we are going to have product of one-dimensional summations. So how's that going to look like? That's going to look like N1 is equal to 0 to infinity e to the power minus beta N1 plus half h cut omega 1 multiplied by N2 going from 0 to infinity e to the power minus beta N2 plus half h cut omega 2 dot dot dot. Once again, all of yesterday's lecture and today's lecture is one page of Chandler. It goes over these things like this. So what can we do now? So the trick I did earlier, I have to do it now. So now we can take this h cut omega 1 and get it outside the summation, okay? But every summation will have its own h cut omega. So this is going to look like, I have to shut my Bluetooth. Oh, this pi day. Anyone wants to challenge me on a pi off?
No,
Not again. I practiced, I revised this morning up to 50 digits. I bothered my wife and Pakoda. Anyway, I would have bought you a pie if you beat me.
Did you get the Cora?
No.
Which distance do we need to run faster than you to get extra grades for this course?
No extra grades. That's not happening. To get extra grades, you have to beat Eric in a 5K, all out 5K. Easy. So this e to the power minus beta h cut omega 1 by 2, this term comes outside the summation. And similarly here, e to the power minus beta h cut omega 2 by 2 comes outside the summation. And what are we left with? We are left with e to the power minus beta n1 h cut omega 1 multiplied by e to the power minus beta h cut, so that's the product for that, omega 2 by 2 summation n2 is equal to 0 to infinity e to the power minus beta n2 h cut omega 2. And we will have 3n minus 2 other such terms. What should we do next? This thing in the summation, that's a series I introduced to you in the very first class. And I vividly remember it was JP who helped me derive the expression. So you should remember. What is this thing?
1 over 1 minus.
So this thing is 1 plus x square plus dot dot dot, where what is the value of x?
Is
E to the power minus beta h cut omega 1, right? And what is the sum of this series? 1 plus x squared till infinity. If x is smaller than 1, if modulus of x is smaller than 1, this series sums up to 1 by 1 minus x. Okay? And the proof for this was to write down s is equal to 1 plus x squared plus dot 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 multiply by x, and you get xs is equal to x plus x cubed plus dot x squared plus dot dot dot. And you subtract both sides and you get that. So we did this in the very first class of 687. So let me write down this equation number 2, the whole summation, the whole product on the next page. So if you have not copied, don't worry. You should not worry about copying anyway. That's fine. So we have q of beta nv is equal to e to the power minus beta h cut omega 1 by 2 summation n1 is equal to 0 to infinity e to the power minus beta n1 h cut omega 1 multiplied by e to the power minus beta h cut omega 2 by 2 summation n2 is equal to 0 to infinity e to the power minus beta n2 h cut omega 2 and 3n minus 2 such terms, right? And each of these, I don't want to erase, each of these is 1 plus x squared plus dot 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 equal to 1 by 1 minus x. Because modulus of x is smaller than 1, right? It's e to the power minus, it is e to the power a negative number. So it's a small number. So we can sum it up and it comes out to be quite nice. So this one becomes e to the power minus beta h cut omega 1 by 2 divided by 1 minus x. So what is x here? X is e to the power minus beta h cut omega 1. So the horrible summation suddenly becomes something really nice. Then you get e to the power minus beta h cut omega 2 by 2 divided by 1 minus e to the power minus h cut beta h cut omega 2 dot dot dot. So all of them are similar. The only thing that is different is instead of omega 1, you have omega 2. Instead of omega 2, you have omega 3, so on and so forth. So I can write down this q in a compact manner. I can write it down. It's pi day, so we use the symbol pi. I'm supposed to laugh. It's okay, it's okay. E to the power minus beta h cut omega alpha by 2 divided by 1 minus e to the power minus beta h cut omega alpha. So we just calculated the partition function. What is this? This is partition function for 3n independent quantum harmonic oscillators with frequencies omega 1, omega 2, omega 3 alpha. We are not quite there yet to talk about heat capacity. We have to do a bit more work. Okay, so again, and I'm following Chandler very closely for this one. Just I'm filling in all the gaps because he does like boom, boom, boom. This is the answer, and he skips everything, which is not good. So we have to do a bit more algebra. Let's call this equation number 3. Yeah, go ahead, Sophia.
So you're saying that x is the e exponential with the negative b?
Yeah,
How's it going x squared, like x cubed?
because it's a summation. N1 is equal to 0 to infinity. Look at this one. Let's write it down. N1 is equal to 0 to infinity, e to the power minus beta N1 h cut omega 1. Okay. So let me say x, let me define x as e to the power minus beta h cut omega 1. Okay, you fine with that? So right now I can write down this summation as N1 is equal to 0 to infinity, e to the power, not e to the power, because I have replaced e to the power minus beta h1 omega 1 with x, right? So this is x to the power n1, right? And what is that? When x n1 is equal to 0, what is x to the power n1? When n1 is equal to 2, what is x to the power n? When n1 is equal to 0, it's 1. Then x, that's why we get it. Okay, clear now? Good. Yeah, please ask questions if something is not clear. So we have this q. Let me write it down on the next page once again, and I will do some simple algebra. So we just showed that q, canonical partition function beta nv, is equal to pi e to the power minus beta h cut omega alpha by 2 by 1 minus e to the power minus beta h cut omega alpha. So now I'm going to do a little bit of algebra. I'm going to multiply, divide this thing by the same thing. I'm going to multiply by e to the power beta h, just to simplify the math and make it look like what you have in Chandler. So I multiply, divide by the same thing. Okay, no one stops me from doing that. It's not 0. So I can do that. When I do that, what do I get? I get product alpha is equal to 1 to 3n, and then it looks like 1, because the product of this and this is 1, right? 1 divided by e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2, right? So if you think about it, what have we just shown? We have shown that if you had one oscillator with frequency omega alpha, what would be the partition function of this one oscillator? Can you tell me on the basis of equation 4? Just remove the product, right? Because the partition function is a product of different partition functions, right? The whole particle. So Q1 would have been e to the power beta h cut omega 1 by 2 minus e to the power minus beta h cut omega 1 by 2. So this is partition function for phonon with one frequency, one fixed frequency, omega alpha. So today we will continue talking about phonons. In Thursday's class, Eric will take one slight step back, and he's going to derive the partition function for bosons and fermions in a more general setting. And when he derives for bosons, you will see an expression very similar to this, with the only change that there will be a chemical potential. And Chandler mentions this, and we'll come back to this after spring break, that phonons have 0 chemical potential. What does that mean? We will get to it after the spring break. But so compare this expression with what Eric derives on Thursday.
You can have multiple phonons with the same frequency, right?
Yeah.
So for this Q1 represents a single photon at frequency.
No, this represents partition function for phonons with a certain frequency. No photon, only phonon.
Yeah, sorry, I meant photon. I misspoke. But I'm just saying that
Photons are actually also similar.
But you don't, in the single partition function, are you saying that, so for any particle in that frequency, the partition function is same? You're not looking at the occupancy of that omega.
So I'm not saying how many phonons do you have.
Right, but when you go to Q of.
So this is phonons.
Correct, but when you go to the total partition function, shouldn't you somewhere consider how many phonons are in each?
Yeah, we are going to get to that in a moment. we can never really talk about how many phonons. That's the thing. You cannot talk about how many photons. Phonons and photons are very peculiar. I can talk about how many students in this class, but phonons are like if you guys just kept one day 0, one day infinite and have no control, right? Phonons are very funky. So it doesn't make sense to control the number of phonons. When we try to prove the counterpart of this thing over here, then we will have to worry about things like that, right? Because electrons are not like phonons. You cannot just keep packing electrons, and we will get to that in a. So phonons are funky because they are bosons. Go ahead.
Can I make a finite number of photons or limited number of photons by using nonlinear material?
You can do whatever you want, but the problem is, even though I'm saying you can have any number of phonons, later I will talk about the average number of phonons, and you will see that the average number of phonons is a fixed number. It's just that you can have higher and higher fluctuations. So if you start making funky materials, you can have more and more phonons, but the probability becomes smaller and smaller. Okay, and we will get to that after spring break. Right now, just stay with this and remember this expression, equation 5. It will show up in Thursday's class and Chandler section 4.4, and Chandler makes a comment. He compares it to the expression we derived for bosons. So we have this, we have Q. We are really going to think about equation 4. How do we go from equation 4 to thermodynamics? What should we do? How do we go from partition function to thermodynamics in StatMech? Take the log, differentiate it, right? This is the recipe. It's really boring. There is nothing. Take the log, differentiate it. If you want fluctuations, differentiate it again. That's what it is. If it looks wrong, multiply the partition function with something, then take the log, then differentiate. It's basically, no, that won't help. If you multiply it with something, it won't help. Log of something multiplied by partition function does not help. But anyway, so long story short, we are interested in ln of Q, right? Ln of Q will be what? Ln of Q will be ln of pi alpha is equal to 1 to 3n 1 by e to the power beta h cut omega alpha by 2. Why is Omar not in class? He's like depressed after the polymer problem in midterm. I was informed he got depressed after that problem.
He just texted Omar is taking spring break.
So depressed that he has gone on. I should have given a pop quiz today. Eric, you feel like giving a pop quiz on Thursday? See me. Huh? I leave it to you.
Share Omar to teach the next class. That's what most of us were thinking when we do the person classes.
No. So, okay, so let's work with this. We have ln of product. Ln of product is the same as sum of ln's, right? Because ln of A, B, C is ln of A plus ln of B plus ln of C. So this thing can be written as summation alpha is equal to 1 to 3n ln of 1 by e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. This is our ln Q. Is it? Yeah, it is. But I can do one more thing. And instead of writing ln of 1 over something, I can write it as ln Q is equal to minus alpha is equal to 1 to 3n ln of e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. Okay. How do we go from heat capacity to this? How do you go from this to heat capacity? Sorry. We're stuck. Why are we stuck? Even more physically, we don't know what to do with omega alpha. We don't know what is the frequency with which these oscillators are moving, right? Are the oscillators doing, or are they doing, we don't know, right? So we have to have a physical model here about the frequencies themselves. We know. So let me call this equation number 6, and I'm going to write it again on the next page. So we have ln Q is equal to minus alpha is equal to 1 to 3n ln of e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. And physically, omega alpha here is the frequency with which atom 1 in a certain direction is moving, right? Something like that. So that's why we have 3n of these. So what we are missing is what values can omega alpha take? And that leads us to the next concept, which is abstract. So pay attention. This is known as density of states. Specifically, we are talking about phonon density of states because we are talking about phonons in the system, right? This is denoted G of omega. And mathematically, it is defined as number of oscillators with frequency in the interval omega and omega plus d omega. So we know there are 3n oscillators, right? And n is probably a large number, right? If it's Avogadro number, which is thermodynamic limit really. So we have 10 to the power 23, order of 10 to the power 23 oscillators, right? So which means that for any given frequency, if you look at a range of frequencies, there might be a bunch of oscillators in that frequency, right? So G of omega counts that thing. So if you really got this correctly, here's a question for you. And I want someone who has not answered to answer. So that means Vedant, Alex, Patrick, JP are excluded. What should be the value of this quantity? Frequency cannot be smaller than 0, right? It does not make to talk about negative frequency. The frequency can start from 0, it can go up to infinity. If I sum this up, what should I get? Nick, what do you think? So G of omega is the number of oscillators in a given frequency range. How many oscillators do we have? So this should be 3n, right? Is it clear to everyone? So whatever density of states you have, this must be true, or you have a problem, okay? Because total number of oscillators is 3n. Now G of omega looks, yeah, go ahead.
Is this still only true under the assumptions we made earlier about them being independent?
No, this is always true. This is always true. We can always. Does anyone know how can G of omega be measured? Scattering, neutron scattering. All these scattering experiments give you G of omega. And I think mostly neutron scattering. So at Oak Ridge National Lab, people have these I think, billion-dollar instruments. And all they do is to give you G of omega. That's what they do. It looks, so, and I'm going to talk, so basically the Einstein model and the Debye model is all about assuming a simple form for G of omega. And we will talk about G of omega in a bit, but what I want to do is to look at equation 6, and this is equation 7, and recast my equation 6 with this notion of G of omega, okay? So equation 6 was summing over every oscillator, right? It was going to oscillator number 1 and saying, hey, what's your partition function? Okay, going to oscillator number 2, taking its partition function, right? And doing the log and summing it over. And because they're independent, you can just do the log of everything and sum it over, right? So now we are going to change perspective. We will switch from, let's call it an oscillator basis, to a frequency basis. And now what you just said, the assumption comes back into play. Now we will again assume that everything is independent. So the frequency along, and if an oscillator is moving with frequency omega 1, it is definitely independent of the oscillator moving with frequency omega 2. That's what we are going to assume. So now what we are going to do is to write down ln q. And this is the step which is, actually, let me do one more thing. So what I'm really interested in is in beta A, right? Helmholtz free energy multiplied by beta. And what is beta A? Beta A is equal to minus ln q. You are all gurus of this, right? You did the homework, you did the midterm, where I think everyone is scoring full, right? What do you think? Midterm was easy? Either?
Oh, man. Yeah, I'd say like maybe difficulty is like 3, 4 out of 10.
Difficulty 4 out of 10.
3 to 4.
Not easiness 3 out of 10.
Wait.
That's okay.
On the easier side.
Okay, so grade your midterm extra hard, right?
Well, I get that extra point, right?
We'll see, we'll see. Why do you get extra point?
If you said I did and Slack.
You did?
Yeah,
Okay, remind me if I forget.
it's already wrote it on the paper.
Oh, good. Then you get it. Okay, so let's look at beta A. So we could have written beta A by equation 6 as minus of that summation. So that would be alpha is equal to 1 to 3n ln of e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. And now we are going to do something which is, I'm going to mark it clearly. When you look at the notes, it's going to be subtle. If you don't understand the notion of switching from oscillator basis to frequency basis, you will feel lost. So instead of summing over discrete oscillators, I'm going to sum over a continuum of frequencies. Okay. And I will replace this with an integral. I will say, well, this is the same as looking at every frequency, counting the number of oscillators you have with that frequency, and then writing down this thing. And now I don't have alpha. I just have to worry about the value of the frequency. I'm no longer thinking about which atom it is coming from. I'm just looking at the value of the frequency. Okay. This is the subtle thing. Is this clear? Take a moment to stare at it. This is where Chandler stops. Chandler derives this. So today's what we did today and yesterday's class was 1.5 pages. After this, he gives an exercise. No, even this he doesn't do. He says derive this. He leaves it as an exercise. Now the question comes, we still need to know g of omega, right? We cannot, StatMech is not going to tell us what is g of omega. G of omega is not, is that Chandler's book?
Yeah.
Okay, what book is that? Okay. When I first time taught this class, there was one student who found it so easy, he would play chess in the class. So I thought you were doing something like that. He is still here. He's in biophysics. You guys can keep guessing who it is. He's in 5th year from India. No more guesses. So this is the expression. StatMech is not going to tell us what is g of omega. Okay, StatMech just derived this expression for us. It's that's why he has a solid state physics book. This is a solid state physics problem. How do you know what is the frequency with which atoms are moving? So let me write down this expression on the next page. And then I will tell you what Einstein did, who was lazy, and what Debye did, who was less lazy. I will show you the final answer. Then we will work through the math. We won't be able to finish the full math today because Eric will come and tell you about fermions and bosons on Thursday. After spring break, we will resume with the math.
Can you just
Yeah.
go over physically why we suddenly switch to the density?
Because g of omega can be measured in experiment. That's the idea. G of omega is something you can measure through experiment. You can measure through ab initio calculations. There are many, many physical tools of measuring it. And and as I will show you, Debye was actually able to come up with a model inspired by classical mechanics for how g of omega might look. So if we just stayed with equation 6, we don't know what to say about omega alpha, right? But if we switch to g of omega, we can do things. For example, do you think, so bug me again in one moment, okay? But let me write down this equation. So we have beta A equal to 0 to infinity d omega g of omega ln of e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2. Okay, and this is equation number 9. So this is a super nice equation. I like this a lot. It does not answer our question. How do we get from heat capacity? So now we have to assume some model for g of omega. So how is g of omega going to look like? So let's think about g of omega versus omega. What do we know about g of omega? Whether the oscillators are independent or not, one thing we definitely know that d omega g of omega should be equal to 3n, right? This is always true because you have 3n oscillators. That's always true. What else can we say? Do you think g of omega can have a finite value for infinite omega? Can you have frequencies with, he's nodding his head, but you're not allowed to answer. No, anyone except Eric is allowed to answer. Can you have oscillator where the frequency of vibration is infinite. Why or why not? Or is there a maximum value for the frequency that you expect in a given material? Go ahead, Alex.
I think we can have infinite omega because we have limited number, limited area under the curve.
That's one idea. What do you think?
I think at some point you begin to dissociate and you
Exactly.
break bonds.
Exactly. You start breaking bonds. Or even more generally, if you have a crystal and you have atoms at a certain distance from each other, certain lattice spacing, or in a chemical bond, if you have the bond length of a hydrogen bond or something like that, you have a certain distance. Matter does not really get on an average closer than, what's the distance of a hydrogen bond? 2 angstrom, more or less, right? Something like that. You cannot have things that are more than an angstrom closer to each other. It will be really uncomfortable, right? Your nuclei will start to overlap with each other. So I'm certainly talking about distance when I was talking about frequency. So what is the connection between distance and frequency? Frequency is something like 1 over wavelength, right? We are thinking about a wave. So as you increase the wavelength, frequency goes down. As you make the wavelength smaller and smaller, frequency goes up. And this lambda is really restricted by something like 2 angstrom. You cannot go smaller than that, right? So since lambda has to be more than equal to 2 angstrom, approximately, maybe 1 angstrom, who cares? Maybe 0.5 angstrom, but really not closer than that, right? So therefore, omega must be smaller than something which is like 1 over 2 angstrom. See my point? So omega cannot be much larger than a given value. It could, but its probability will start to become smaller and smaller. So if you were to do a real like neutron scattering experiment, G of omega curves can look complicated. It might look something like this. I just drew something. It could look it, and these things, they would correspond to some phase transition in the material, right? The things where, that's why neutron scattering is also very important. You made some funky material, you want to study whether it is one phase or not. And by studying the G of omega, you can get clear signatures of whether it moved from one phase to another. So, but generally it will go to 0 at some omega. You cannot have a G of omega which keeps diverging. That we already know due to what Alex said and this equation, right? The area under the curve has to be finite. But even more physically, it has to be smaller than a certain number. So this is some generic experimental G of omega that you can measure from, let's say, I keep saying neutron, I'm just going to call it scattering, some scattering experiment, you can measure this. Einstein was super lazy. He's laughing. He was. He said, you know what? I don't know. Let's just say only 1 omega is possible. Okay. Let me draw a thick line for it. He said, let's say only 1 omega is possible. And he called it, well, I'm going to call it omega Einstein. Okay. So Einstein said that only 1 frequency possible. It's a terrible approximation, right? Why? Basically, he's saying that atom 1, atom 2, atom 3, direction 1, direction 2, direction 3, whatever, everything is moving with the same frequency. Why did he do this? Because it makes the math very, very easy. Now you can write down G of omega is going to be proportional to a delta function of omega minus omega epsilon, or omega Einstein. And why are delta functions nice? Because they make calculating integrals super easy, right? What should be the proportionality constant? Someone who has not answered. Suleiman, what do you think? No, your hint is this equation. 3n. So G of omega will be 3n delta of omega minus omega e. You can check yourself. If you integrate this from 0 to infinity, then you will get 3n, right? So you always want that to happen. So that's Einstein's frequency. let me draw this again on the next page and I will talk about both the frequency models. So, and I'm not going to draw the real curve. So we have G of omega versus omega. Einstein says, well, I'm super smart, but I'm also very lazy. So I will just say that only one frequency is possible. So as per Einstein, G of omega is equal to 3n delta omega minus omega Einstein. Debye. Was Debye before Einstein or later? He was later. We won the Nobel Prize in like 20s or 30s, something like that, right? Debye was later. Debye said, you know what? Einstein, stop being lazy. Debye said, the frequency of states is going to look something like this. It will rise as a parabola. So zero frequency means infinite wavelength, right? We will have zero probability of something like that happening. As you increase the frequency, the probability will increase. Then it will get to a cutoff because we cannot have exceed frequencies which are, shorter than the lattice spacing. So he said, let's call this as omega. You guessed it, Debye. I don't think those guys came up with the subscript, but that's what we are going to use. So Debye said, G of omega is some constant, we are going to call it K Debye, omega square, omega less than equal to omega Debye, and 0 if omega more than 0. How do we calculate the value of KD? Again, by using the same integral, right? We know if we integrate it, we should get the value of 3n. And we will do all that math, but I want to tell you the results that come out of both of these, which we are going to derive, so it's important to look at the final thing. Oh yeah, you're paying attention. Omega Debye. Okay, so we will start plugging through the math, but what we will find is that as per Einstein, the heat capacity. So first thing we will see that for both of the models, the heat capacity shows 3nk as t tends to infinity. We will see this, okay? Even for this one, CV tends to 3nk as t tends to infinity. The question is, does it correct the zero temperature behavior? What curve do we get? For Einstein, after all the math, we will see that CV is proportional to, if I'm writing gas constant here, which is Boltzmann constant in another unit, it comes out to be 3R multiplied by theta E, which is related to omega E. Don't worry about the prefactors here, just look at the term, the temperature terms. While the Debye expression for heat capacity, and again, if this looks to you, where did this come from? Well, it will take 2 pages, quite a lot of algebra to get there, which we'll just work through. Debye's heat capacity turns out to be 3nk pi to the power 4, believe it or not, it's really pi day, multiplied by 3 divided by theta d whole cube multiplied by t cube. So bunch of prefactors multiplied by t cube. So Debye gets it right. So if I was to plot, let me plot it over here, because I don't want to switch the page. The heat capacity versus temperature for the Einstein model and the Debye model. So both of them show the right behavior as temperature goes to infinity, right? Both of them become constant. You will see through the algebra. The question for you now is, which one goes to 0 quicker? Which one will fall down faster? Einstein or Debye? Einstein. Don't look at the math. You can see it from the math. Why from the math? Because it's got an exponential, right? Exponential. Even though, so Einstein, there is a competition. In the numerator, you have an exponential, which is saying go to 0. And in the denominator, you have t squared, which is saying blow up, right? But as t becomes very small, exponential dominates. So the Einstein thing goes to 0 a bit too aggressively. Something like this. While the Debye thing actually shows the 1 over t cube behavior. That's what we are going to see next. And that's mathematically. Physically, why does this picture make sense? Given the g of omega plots that I drew, why is it that the Debye model falls down gently? Why is it that the Einstein model heat capacity goes to 0 a bit too aggressively?
Because the frequency is not temperature dependent, like you don't need to heat the crystal.
Yeah, but I mean, yeah, so Einstein model allows for only one frequency, right? And as the temperature goes to 0, and if you start thinking about KT compared with h cut omega, right? You start to fail because h cut omega E has only one particular value. So your temperature, the quantization starts to play a role very quickly. While in Debye model, omega can take any value, right? There will always be a way to excite the system. The heat capacity will go to 0 as you go to t tends to 0, but it will start to rise a bit quicker as related to Einstein. So it's a subtle point. And yeah, any questions? Anyone has any idea why does the Debye expression have this peculiar pi to the power 4?
Gaussian integral or something.
It's all, well, sure.
That's why probably-
So it will come later. But Debye things actually gets to an integral which shows up in solid state physics quite a lot, which is 0 to infinity e to the power x, x to the power 4 dx by e to the power x minus 1 whole square. And this integral, for some reason, is 4 to the power pi 4 by 15. It's pi day, so we have to respect pi. Okay. There was this Indian mathematician, Ramanujan, who would derive integral expressions like this, like out of his ass. You know, I don't know how to prove it, but it exists. Some of them would be terribly wrong, and some of them would be correct. And he had one such expression, which is still like one of the quickest ways to calculate pi. So we all know that a good approximation to pi is 22 by 7. Do you know a better approximation to pi? Anyone remembers? Don't tell me 314 by 100. No one remembers. It's a this one. Don't write it down in your notes. It's okay. This one is okay till like 9 digits, and it comes from one such series, which is very interesting. So 8 or 9 digits, 350, and it's easy to remember, right? 113 by 3 first. I was really hoping we'll have a pi off. Can only dream, right? So this is the physical picture, and long after this course, you will forget the math that's going to follow next. This physical picture, I hope you remember, right? So what have we shown so far? And I'm going to stop here because I don't want to start like math in the last 5 minutes. We will do math after spring break, or I might just give it to you for homework. We'll see. It is a problem in Chandler. So
Is there a better textbook in Chandler?
what?
Tuckerman.
Tuckerman is good. Tuckerman's book does a good job. And so Macquarie is a good book, but Macquarie takes the Gibbs entropy approach, which I do not like. Tuckerman takes the same Lagrange multiplier approach. A book which I like a lot is a book by Scott Shell, but Chandler still exists to be, it's not the best possible book that could be written, but it's quite good. But you are coming to my class, so you don't need anything. So let's look at the physical picture of what we have done over here. So we are interested in figuring out how does the heat capacity in a material, in a chemical look as a function of temperature, right? So what does heat capacity come from? It comes from, well, capacity for heat. You give heat into a system and you see how does the temperature change. So in order to model this, we had to come up with a very simple model for a material or a chemical. We said, if you have n atoms, everything is moving in independent directions, and let's assume every direction is independent of every other direction. Every atom is independent of every other atom. Let's model everything as a harmonic oscillator. We modeled it as a classical harmonic oscillator, and we derived the heat capacity. It came out to be constant, right? You got the ideal gas answer. Then we said, well, okay, that's bad because we expect that there will be quantization. At 0 temperature, you cannot just give some energy and expect that the material will respond to it. Because if the energy is smaller than the minimum quantum, h cut omega, that energy is useless, right? It's like me giving Eric half a penny and telling him go buy a candy or a supercomputer or something like that, right? Half a penny is useless. I have to give him at least 1 penny for him to be able to. Huh? Half a penny, you won't be able to invest even wisely. What will you do with it?
I don't know, lots of things.
No, you cannot buy Bitcoin with half a penny.
You could have bought Dogecoin a couple years ago, and that's
Dogecoin.
9 cents. But then you can invest that in some big stuff.
But even then, you would need quantization. In order to make an account to buy Dogecoin, you would need a few quantum of energy, of money, right? You would need at least 1 penny to do anything. So that's how it is. So we need quantum mechanics for the heat capacity to go to 0. So we said, okay, these harmonic oscillators still assume they are independent, but now assume they are quantum, which means that the energy eigenvalues are now quantized. You have a set of eigenvalues. So we derived the partition function for this. We thought about every atom separately, every oscillator separately. We got an expression which looks like equation number 6. And then we said, let's switch to a density of states basis. So G of omega captures the number of oscillators with a given frequency. And we can talk about this because we are going to work in the thermodynamic limit where n is very, very high, right? If n was 5, then it would be kind of pointless to talk about this. We switched to G of omega and we wrote down an expression which looks like this. And now we were stuck because StatMech does not allow us to calculate G of omega. We have to assume some solid state physics. So we went to Einstein, who said, well, just assume one frequency, which is omega e. That gives you a delta function. And I showed you the answer. If you plug G of omega is equal to this thing into equation number 9. Equation 9 is all you need to get these results. It's just algebra, nothing else, only algebra. So equation 9 will show you, you put in G of omega, you do the math, you get ln A, you differentiate, you get entropy, you differentiate it, you get the heat capacity, you will get this relation. Einstein's heat capacity goes to 0, but a bit too aggressively. And that's because Einstein assumed only one frequency. Debye said, and this omega square you can read about books. The best way to read about this is, there is a book which I like a lot, which I say, as I mentioned, is one of the most famous book that everyone tweets about, no one talks about, reads actually, the States of Matter book by Goodstein. He goes into this derivation very, very carefully. And I think the solid state physics book by Rife, sorry, thermal physics by Rife also talks about this probably, but I will put a question mark, I'm not sure. So this omega square really comes from continuum mechanics. There is a reason why Debye was interested in frequencies in a continuous material, if you assume continuum mechanics. So there is reason why he took omega square, because if he had taken omega to the power 4, he would not get this T-cube dependence. He had to take omega square to get this. So we'll work through this after the spring break. Thursday's class will not be on Zoom. It will be only in person. I won't be here. Dr. Bayerle, who's world famous expert on statistical mechanics, will be teaching you how do fermions and bosons look like. The math will be a bit less gnarly than this one. And pay attention that you will see a chemical potential. So when he teaches you, argue with him, give him a hard time to compare this equation 5 with respect to whatever he derives next time. Okay, stop him, treat him as kindly as you treat me. Any other questions? Okay, so see you after spring break. So the first, right after spring break, there will be a massive homework, okay? Big one. I might actually make it a 2 homework. Who wants that? So, okay, raise your hand if you want long homework worth only 1 homework. Who wants that? Or a longer homework worth 2 homeworks. Okay, I will have to poll on Slack. Okay,